Alrighty, the last part of 8.5 finally. Woo! Okay, so we're doing strong acid, weak base. This is very similar to scenario 2, so theoretically this should be faster. Alright, and so here is the problem we're going to analyze real quick. Let's talk about generalities first. So we know that hydrochloric acid is ionizing completely because it's a strong acid. And so I skipped pretty much the regular reaction and complete ionic, so I just went straight to net ionic. Again, this is similar to the previous section with the same scenario, so, same thing. And we removed the spectators as well. So here we have our weak base. And then our H3O plus, that came from the H plus here, because remember H plus isn't chilling by itself. It is hanging out with water. And so we have hydronium, and then we equilibrium to ammonium ion and water. And so our generic B is base, don't forget. And then here's the conjugate acid. So there we go. And so again, this graph is going to be similar to the previous scenario, just a little bit, different based off what we're starting with. And as a reminder, the conjugate acid, which is the BH plus, can act like, an acid. And so that H can be donated to the water, and then you have the base and then the hydronium ion. So here we are looking at this graph over here. And so again, very similar to the previous scenario, just flipped because we're starting with a base because we are over 7. And so E is the equivalence point. We've talked about that before because it's in the middle of the vertical line. So there we go. And so it's dependent on the conjugate acid and its Ka. So we got this formula from our constant equation sheet, Kw. Oh, I forgot to change this actually. It's Kb. Oh well, whatever. And so, oh man, that's annoying. Oh well. So, use the conjugate acid, the Ka of the conjugate acid, then we got the Kb, hooray. And then we have the initial pH here at A, and so that's based off the conjugate, I'm sorry, not the conjugate. It's based off the base concentration initially and the Kb value, so we would look at those to get that. And then C is halfway between the to the equivalence point, and so that means our base is equal to its conjugate acid, and so POH equals PKB, pH equals pKa of the conjugate acid. So you want to be careful of the K value versus the Kb value. Okay. And then F is our pH after equivalence, so that means we have extra acid here, and so the extra acid is what's going to control the pH. Our buffering region is this region BCD area, so make sure that you can recognize that on the graph. And so we have more base compared to conjugate acid at point B, and so our PKB is going to be more than POH, and so we would use that to determine the pH eventually. And then the opposite is true for point D. Perfect. So here is the different images that represent different points of the graph. Make sure to use this key here. Look at all the letters. Decide which letter is to which number. So pause it. Are we ready? Here we go. Cool. So here's my explanations here. I'm not going to expand on it, so pause it if you need it. Make sure that you could draw this if it was given to you on FRQ. Make sure you can decide which image makes sense if this was an MCQ, because they definitely could be questions asked. So just be very careful about that. Cool. All right. So we're going to go through this example. Again, very similar to the previous example, except, opposite, where it's weak base, strong acid. And so again, similar situation. So pH of the initial solution, we're looking at just the weak base right now. And so I wrote down the reaction in our rice table. And so remember, we don't fill out water because water is a liquid. And we are starting off with 0.2 molar because that's what was given here. And we initially don't have this. But there is equilibrium in how much ionizes, so we do our little X's here and then our subtracting because this is converting to that side. And so if I check the Kb value, I multiply that by 100, it's still less than the concentration of the initial reactant, and so that's why I rounded this here. And so I pretty much am just going to plug in my values based off the E part of the rice table and then the Kb value given up here. So again, it's just a rice table problem. I solve for X and then I get my value for X. Cool. And so once I have my value for X, and notice it's a hydroxide, and so I can calculate the pOH by plugging in my X value, because again it's right here, it's the same, and I get my pOH. So then I can get my pH by doing the the equation that's given in our constant equation sheet. pH plus pOH is 14, and so I rearrange it to get my pH, and then boom, got my pH. So make sure you can do that. Cool. All right, if we add 25 mils of HCl, cool. Now, one thing to notice real quick is that we initially started with 50 mils of the weak base versus the 25 mils of the strong acid. So because of that, we're halfway to the equivalence point. Now, if you didn't notice that, that's fine. You could just use the HH equation just fine if you didn't notice that. But since I happen to know its equivalence point, because again 50 versus 25, then I can go ahead and just use pOH equals pKb because that cancels out the plus log of the amount of conjugate acid to the weak base, and so that's why these can be equal. And so I just plug in pKb and then boom, and then I use this equation from earlier, pH plus pOH is 14, and then I get my pH value. So cool. So regardless, if you're not sure if you're halfway to equivalence or not, just use the HH equation, plug in your values, do a rice table, so cool. Okay. Now this question is slightly different. It's saying what is the volume of acid added at equivalence? So we don't know the volume of the acid, but we have to figure that out. So we know different values, right? And so we're going to go ahead and do that. And so you can use this from, I forgot what unit it was, but it was some unit ago where we were looking at titrations. And so I could just plug in the values for the acid versus the base. So here's my acid, here's my base. And so I could solve that. And so I got my volume of the acid. Cool. And so at this point, this is, as I said here, all of the acid reacted with the base. So now we have the conjugate acid, because remember the base is going to act like a base. And so all the base we have changed to make this conjugate acid. And so in order to see how many moles of conjugate acid we have, we use the liters that was given here, just convert it. Then we have our molarity, which was given here. And so I have that. And so my new total is adding everything together. So we found out 50 mils of the acid. We had 50 mils of the weak base. It equals 100. And so I can get my molarity of the ammonium ion. And so then I would use the formula that is given on our constant equation sheet. I plug in Kw that's given also on the constant equation sheet. I have my Kb value, which is right here, and then I can get my Ka. So then I fill out a rice table because again, the conjugate acid will act like an acid. And so this NH4 is going to donate an H to water, and so we're making ammonium and hydronium. And so we fill out our rice table. We're going to do the same thing as before, where we check if we can do the shortcut. We indeed can, because that is hella small. -10, multiply that by 100 is still a very, very small number at 10 to the -8. So I can round this to about 0.1. So I'm going to set up the situation like before. We have our Ka, we have our value of Ka right here. I have my weak base my hydronium, and my conjugate acid. I'm going to plug in my values. I got x squared on the top, and then I got 0.1 from here, and then it's equal to the Ka that was given here. I solve for x, I get that. That is my hydronium concentration, so then I can use that to get pH, because pH equals negative log of the concentration of H plus. And so I'm taking this, plugging it in, got my value. Cool. Easy peasy. Hypothetically. Okay. And then we have the pH if I added 70 mils instead. So new total is 70 plus 50, as you can see here. And so if you notice, we are going beyond the weak base. So we're going way beyond. We have acid. So we learned from the previous problem, 50 mils is at equilibrium. So we're seeing how much leftover excess acid we have. So I subtract those to get 20. And so then I'm going to use that 20 in order to figure out how many moles of H3O plus I have from HCl. So that's what's here. This is from the molarity given earlier, the 0.2 up here, and then the volume right there of the amount of acid. And so that is the getting the concentration of the H plus, which is inherently getting the concentration of HCl, because they're 1-to-1. For every 1 mole of H plus, I have 1 mole of HCl. And so I got my molarity there, and then I just plug in my molarity based off pH. Cool. All right. Cool. So here is a practice problem. I wrote some hints down for you. So try it out. Pause the video. Ready? Here we go. Now, I personally didn't check earlier if I was halfway to equivalence point or not, because I didn't. I almost never do, personally. So I just use the H equation as is. If I noticed it was halfway to equivalence point, then I could have saved a step, which, again, it's a little bit of a save, but like not too much. So honestly, it's however you want to do it. So here is my work shown. I highlighted some parts so you could see where some of the values are coming from. I noticed I didn't highlight this in a color that's very obvious, so be careful on that. And so I could have set up a BCA table, but I didn't, so I just talked about my logic here. Again, BCA table is helpful if you want to organize your thoughts. I didn't, because I wanted to show another way of doing it. I already showed how to use a BCA table in the previous examples on a previous video, so I'm just showing another way. Cool. So this is one part. Go ahead and pause it if you need to, and then going to the next slide now. And so here you go. Oh, I did show a BCA table. Oh, I guess I did. If you prefer the other way of solving it. I forgot. So here's the other way of doing it. Cool. And then here's my BCA table. Boom. So that's the example problem, your turn. So hopefully you understand it. Please ask questions if you don't. Okay, so summary of this whole section, right? We just went over a whole bunch of stuff in 3 different videos. So you use the HH equation when you got something weak. So make sure you know that the conjugate is on the top, and then whatever the weak acid or weak base is on the bottom. So just make sure you know that. And the first equation is on our constant equation sheet. The second one is not. The assumption is you can convert the HH equation. If you have weak base instead, you have to logic it out. So instead of pH, it's POH, because we're talking about a base. Since it's an acid, it's Ka versus Kb is for a base. So like logic it out, pretty much is what they're saying. Now, obviously you could just memorize it, but personally I just use the HH one and then change it as needed. Make sure you're looking at what's the titrant and the analyte. What is the strong thing versus the weak thing, or do you have 2 strong things? Be careful. Knowing where that buffer region is, both on the titration curve as well as just looking at the problem itself, very handy. Again, look over 8.4 with the drawings. In this last example, I went a lot quicker because, again, it's similar to what we've done before. So make sure you look at the drawings from 8.4 and this section, compare it so you can see how the drawings relate to these problems because they come hand in hand, okay? And then, like it says here, it eventually clicks as you get it. The biggest summary / tip for this section is looking how many moles of the acid versus the base you have, because then you see what neutralizes. If I neutralize an entire something, like if I neutralized all of the weak acid, that means all of it is now the conjugate base. And so that will affect my pH because the conjugate is going to act like a base, and so it's going to, do its thing. So just be very, very, very mindful of that. Like, that is what we did in all the calculations. Cool. As I said here, calculating the equivalence point is helpful to do before actually solving any FRQ problem. It's good to do just to give you a reference, so as you're calculating, if you see you're over the equivalence point, then the calculation becomes easier because that means you have extra of the titrant. So just be mindful of that. Okay, so that's it, finally, for section 8.5. Bye!